Okay, so any questions over chi-square goodness of fit test? Have you started looking at the homework problems? Emily, I know you did because you've already emailed me there's a problem. Anybody else? And you should also be looking in the book at the problems at the end of each section, just to prepare yourself for exams, and also the examples in the book. They'll be similar to the homework problems. If you can go through the examples without looking at their solution, then look at their solution, that's a good way to study. You know what I mean? So I was going to go through real quick one of the homework problems that I know is in the online homework, on the Launchpad homework. In the book, this is example 915, and they also have a homework problem made out of this that then I used in Launchpad. And it's a categorical one. So the scenario here is sampling in the Adequate Calcium Today ACT study. Right? So they did this study on whether people were getting adequate amount of calcium in their diet to promote bone development and so on. They had participants, 14,000 participants in this study. Okay, and they come from 6 states: Arizona, California, Hawaii, Indiana, Nevada, and Ohio. So they have this contingency table: Arizona, California, Hawaii, Indiana, Nevada, and Ohio. Then it says, after the major goals of the study were completed, the investigators decided to do an additional analysis of the written comments made by participants during the study. Because the number of participants was so large, a sampling plan was devised to select sheets containing the written comments of approximately 10% of the participants. And this is fairly common when you have really big studies, that you want to do more complicated analyses of the data, but there's too much data. So I need to pick some of that data and do this analysis. If they're looking through comment fields, can you imagine doing comment fields and processing that data for 14,000 questionnaires that you get back or whatever? So we want to do 10% of that, so around 1,400. Okay, so they do a sampling scheme, and they draw a random sample, and in that random sample, they get these counts: 167, 257, 257. My handwriting doesn't look good on this, but I assure you it's the board, not me. 107 and 482. And that was a total of 1567. Okay, so their sampling scheme didn't get them exactly 10%. It got them a little more than 10% of the 14,000. Right. Okay, now, in the original sample, they give us the percentages that came from each of the states. All right, so in Arizona, of the 14,000, that was 10.5%, so 0.105, and 0.172 came from California, and so on. do a chi-square goodness of fit test to see if their sampling scheme was able to mimic what was true in the full sample, the 14,000. Okay, so tell me what to do.
You need to do the observed minus the expected squared divided by.
Okay, so we need to form a chi-square test statistic by taking observed counts minus expected counts, quantity squared, over expected counts in each state. Sum them up, right? I don't see expected counts on here.
Well, you need to take 167 times 0.05 and 257 times 1.72.
Okay, almost, but not quite right. What did he say wrong?
You take the total times those ratios.
Right. You said take this times 167. This is observed count. Expected would be 10.5%, 0.105 times the 14,000. Right? So you take each of these times 14,000, and this will divide them up into, divide the 14,000 up into the particular states, and that's what you would expect to get. Yep.
Take it down to 14,000 or like the 1567?
Yes. Yeah, thank you. What I said is actually right, but it isn't what you want as expected counts. What I said was you take 0.105 times the 14,000, and that's how many you had in the original sample from Arizona. Right? So I said that's what the actual counts in the original sample were, but that's not the expected counts for this sample. That's going to be way too big. So you take what Leanna said, take this number times the total sample size in your subsample, the 15. So just to illustrate, I'll write it out for this first one. 105 times 1567, and that's the expected count for Arizona. And then you do the same thing, and it's 1567 all the way across. What's that?
You ready for it?
Sure.
It's 164.535.
164.535.
269.524.
524. I can't write small with this. So this one goes here.
256.988. 294.596. 109.69. 471.667.
Okay? If I sum all those up, what do they sum to? What should they sum to? They should sum to 1567. Now there may be a little bit of round off error since they only gave us these proportions to 3 decimal places. Sometimes it won't be perfect, but that's okay. If these proportions sum up, they should sum to 1. Right? Therefore, these should sum to the total 1567. Does everybody understand the way I tried to alternate here so I could fit them all in? Okay. Now, rather than make you do this on your calculator and sit and wait for you to do it, does everybody understand now what you would do? You're going to take the observed count, 167, minus the expected count, 164.535, quantity square that, and then divide by 164.535. Write down that contribution to the chi-square test statistic, and then do it for every one of the states, and then sum those contributions, and you get some number. And I can just read it from the book. Well, I thought I could read it from the book. There it is. It actually goes into the next example, example 916, where they give you the answer. Right? Here they give you these expected counts and then call it good. So the final value, the sum of the 6 values, is the chi-square test statistic, and that is chi-square equal 0.93. Now, I told you before, the chi-square test statistic doesn't have any intuitive appeal to me. I can't look at it and go, ooh, that's really big, or ooh, that's really small, except one like this. What do you think about that number? 0.93.
That seems.
That's really small.
Oh, really?
So, yeah, that's really small. The chi-square test statistic, the mean of a chi-square is its degrees of freedom. You don't have to know that, but you'll learn that in MA343 if you take that class. The mean is its degrees of freedom. So what is its degrees of freedom here? 5. There's 6 states, so 6 minus 1 is 5 degrees of freedom. So the mean, where the hump is for a chi-square, is 5. So this is way below the mean, and it's the right tail area that is your p-value. So we're going to have a really big p-value here, right? Do it on your calculator. Do x square CDF, chi-square CDF. So push the second function button, and then the vars button, which has DISTR above it. Go down to chi-square CDF. You're going to enter this value as the lower bound, then infinity, so a bunch of 9s for the upper bound, and then 5 for the degrees of freedom. And that'll give you the p-value. And what is it?
0.968.
0.968. Right? So 96%, now almost 97% of the area under the chi-square curve has been shaded when I go from this value up. Right? Now what is the p-value again? I always forget that. Okay. Probability we could get results like we got, the observed results, if the null is true. Now what's the null? That it's a good fit, right? That the null is that the proportions we got in our sample are equal to the proportions we would have expected from our full population, right? So the probability we could get numbers like we got, if they really exist like this in the population, almost certain. So there's no reason to reject the null. We say, yeah, the data it's a good fit. We do not reject the goodness of fit. Right? Now I mentioned last time that the null and alternative hypotheses in a goodness of fit test are really flipped around from what we're used to. Usually the null is what we hope to disprove. We hope to prove the alternative. Here it's flipped around the other way. But the reason it's flipped around the other way is because the null in a hypothesis test always gives you values that you can use to compute probabilities, called p-values. The alternative is just that, well, that's not true. Right? So if I say, well, this is not a good fit, and I use that as my null, how would I compute probabilities of getting data like this if all I know is, well, it's not true? I don't know what the proportions are. Well, if I don't know what the proportions are, I have no way to compute the expected counts. I can't do the test statistic and all that. So I have to do it this way. Right? It's not ideal, but it's the best we got. Now, some of your calculators have a chi-square GOF test in them. Right? So you can, I'm not going to teach you how to use that, but you can figure it out on your own. Not everybody has, I don't think you do. He's got an 83, and the older 84s I don't think do either. But if you push stat, then tests, and go down, see if you have the chi-square-GOF test. If you do, you can put these observed counts into a list, and I think you then have to put the percentages, these percentages, into L2. I think's how it works. I haven't done it in a long time, but you can play with that and see what you do. The one that I will give you on an exam will be one that's fairly small like this, where it's pretty easy to do by hand. So, okay, any questions?
The chi-square, so how do you get to 0.93?
That's from,
That's expected, that's expected?
no, the 0.93 was the sum across all categories was observed minus expected. I want to use my finger. Observed minus expected squared over expected, summed across all those cells. And I didn't spell cells right either. Right? Okay, so those numbers that we wrote down there for expected counts, you do this with the expected counts for all 6 cells and sum them up. So the fact that it only summed to 0.93 means that all of them were pretty close to what you would have expected. We were getting really small differences there. Okay? All right, so let's move to the next topic at hand, and guess what that is? Your first project. Have you been looking at the syllabus? See, I was guilty of not really looking at the syllabus until yesterday, or I would have said something about it Monday during class. That, oh, we got the next project. It's a chi-square example for a project. And so, actually, I'm not sure if I've posted it yet out there for on D2L or not, but it will be as soon as I get out of class. But what we're going to do is we're going to divide up into groups, and then you're going to work together as a group to answer a series of questions about a study that was published in the New England Journal of Medicine. And it's a very interesting example because it uses chi-square tests all over the place. So let me get that up. And then what we'll do, what I wanted to do, but I forgot on Monday, was to have you individually do the first few questions on this and then be prepared today to finish it up. But instead, we're going to work together on all of them, and it may take us till Friday to get this thing done. Right? So here's just some background on the article. Let me also pull up the article itself. And both of these will be available. You'll need to look through the article to answer some of the questions. So this is an electronic copy of an article that was published in the New England Journal of Medicine back in 2003. And it's called A Comparison of Magnesium Sulfate and Nimodipine, I'm not sure how to pronounce that, for the prevention of eclampsia. Now, I don't expect you to be up on medical terminology and all that stuff, so don't worry about that part of it. In the other document, which is kind of the instructions document, it gives you some background, and you'll want to read through it and get a little bit of an understanding just so that you can understand the questions that are being asked. But eclampsia, it says, is a very serious condition, can arise in pregnant women. It involves seizures and can be fatal, right? So very serious. So it says there are warning signs, and that's known as pre-eclampsia. So if certain things start to happen, then ooh, they're going downhill pretty quick here, and they can take action and prevent those seizures. So the authors are comparing magnesium sulfate to nimodipine, I think is how you say that, right? And so magnesium sulfate is the kind of standard treatment that has been in use, and this is a new one they want to compare to that. Okay? So here's a glossary: postpartum, neonatal, cerebrovasodilator. Right? That means to make the blood vessels bigger so you get more blood through. Right? I won't go through all these, but you'll need to read them. But just some background as you go through it. So the first 5 questions are what I was going to have you do individually, but you can go ahead and work together on them. Main objective of the study: what are the variables in the study? And of course there's lots and lots of variables, so name the important ones. What's the explanatory variable? What's the response variable? What are the important confounding variables? The ones they want to control for. Things like that, right? Is it an experiment or an observational study? Remember those terms from MA343? If an experiment, what was the design? What did the authors conclude about the primary outcome measure? And what about secondary outcomes? So the primary is the main focus, right? Just whether or not did they get eclampsia. But then they also measured other things, like maybe blood pressure. Maybe, who knows? But read it and see what the secondary outcomes were and what their conclusions were. And then Table 1, it says, what does Table 1 have to do with this report? Why did the authors report on these variables? So I'll bring up Table 1 in just a second. And so then after those first 5 questions, which are basically background of the article, now you start having to compute some stuff. So the p-value is this. What does that mean? What test did they use? P-value, interpret this p-value. And then finally down at the bottom, calculate the p-value that they have in the table. I want you to show that, hey, I can do the same analysis they did. I'm just as smart as them. Right? And make basically interpretations of the article. Okay? The last part here talks about relative risk. And every day when I come to class, I say, oh, okay, I got to remember to talk about relative risk, but I still don't think I've done that. Have we talked about relative risk? Some of you are going, a little bit. But relative risk in a two-way table, let me go over on the whiteboard. In a two-way table, lost my follower here. So let's say we have drug 1, drug 2 as the rows. So that's magnesium sulfate and nimodipine, or whatever it was, right? And then we have eclampsia yes, no. Right? If you produce conditional proportions of eclampsia for the two groups, conditioning on which drug they got, let's say we have, let's make up some numbers. Actually, yeah, let's make up some numbers. Let's say we had 23 women in that group and let's see, 477 in that group, and I tried to do the math in my head, so that adds up to 500. Does it? Okay. And then in this group, let's say we have 17. Right? So then that would be 483 to get 500. So in this particular made-up table, I've got equal sample sizes in my two groups. So give me the probability of eclampsia given drug 1. Okay, it's 23 divided by 500. And what did you say that is as a decimal? 0.046. So just a little under 5% of women on that drug went on to develop preeclampsia, or eclampsia. Probability of eclampsia if drug 2, 17 out of 500, which is 0.034. So think of these numbers. They are probabilities, or they are proportions, conditional proportions, but also think of them as estimates of the risk. The risk of eclampsia if you get drug 1, the risk of eclampsia if you get drug 2. The relative risk is then the quotient of those. Right? So usually we put the control group, the standard therapy, on the bottom of the fraction. But doesn't matter. But in this case, let's do relative risk, RR, for D1 versus D2. That's saying I'm going to put D1 on the top and D2 on the bottom. That's going to be 0.046 divided by 0.034. So, RR, you'll see a lot of references to the term relative risk, but you'll also see other books, other articles that'll call it risk ratio. So RR can mean, and it's the same thing. Right? So what is this number?
1.353.
1.353. So how do I interpret that number?
Drug 1 is 1.353.
Good. Women who got drug 1 are 1.353 times more likely to get eclampsia than women that got drug 2. Now, if I put a confidence interval on that, a 95% confidence interval for the population relative risk, and let's say it goes from 0.92 to 1.73.
Statistically significant difference because the 1-to-1 ratio means it's the same.
Exactly. You're looking to see if 1 is in that interval or not, right? Because 1, a relative risk of 1 means, hey, they're the same. They have the same risk. That would be your null hypothesis. No difference between them. Oh, ratio is 1. If the confidence interval excludes the number 1, then you say, oh, there is a significant difference between them. So if this, instead of 0.92, if I got 1.02 to 1.73, then this one is a significant difference. So this would be p-value less than 0.05. This would be p-value greater than 0.05. All right, remember there's a one-to-one correspondence between confidence intervals and p-values. They have to make the same conclusion. If this rejects the null, then this has to reject the null. Right? Well, the null here, the null value is 1. This rejects 1. This fails to reject 1. Okay? So that's what this one's talking about. Table 4 gives risk factors for seizure. Talks about adjusted risk ratio and things like that. But and I have some verbiage in here about, don't worry about what that means. That's kind of beyond the scope of this course. But the relative risk for nimodipine is 3.2. Interpret that. Give your conclusions based on that. Okay? All right, so I'm going to turn off the video now, and we'll get